So today we're looking at extrema of polynomials. So first thing we have to do is figure out what extrema are. All right, extrema are the peaks and valleys in a graph. All right, so the max and mins of a graph. So here we go. So let's say we have a graph that looks like this. All right, so the peak or the maximum is going to be there. There's a peak. Here's going to be a valley. That's the minimum. Okay, so those are two examples of extremas, a peak or a valley. Could be both. Okay, so let's look at some examples of these graphs with different polynomials. So let's say we have a fourth degree. Fourth degree means you have an exponent of 4 on a variable. So here's an example. We have fourth degree polynomial. There are other examples. This is not the only type, but here's an example of one. Boom, 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 boom. There we go. Notice it has 2 valleys and 1 peak for a total of 3 different extrema. So we have 3 extrema. Okay. All right, let's try a fifth degree polynomial. You'll have something that's raised to the 5th power. Give me another example. This is an example of a 5th degree polynomial, x to the 5th. Okay, so it's raised to the 5th power. In this case, all right, you have, we're going to say this is a 0. This has 0 extrema. Okay, there are really none. And here, let's go through another one. We have a 6th degree polynomial, so something raised to the 6th power. And you have something that looks like this. And we have a bunch of different peaks, a couple different valleys. We have a total of 5 extrema. So, oops, I spelled that wrong. So what we're going to do is figure out, like, is there a way we can figure out just by looking at an equation how many extrema it might have? And there is a way, so let's look at some of these examples. All right, and the first thing we want to look at, looking at these examples, is the types of functions you might see. So we have linear functions. In this case, there are 0 extremas in this because, well, there's nothing there. Okay, there's no peak, no valley. So it's going to have no extrema. You got quadratic functions, okay? So something being x squared, like, say, for example. All right, there's a valley here, there's a peak here, so they might have 1 extrema. Cubic functions, okay? The first example, the first 2 here, these don't really have any extrema. There's no peak or valley. It just kind of like squiggles, but it doesn't really, there's no high or low point for those peaks or valleys, so that's not really going to have any. So these are examples of zeros because this part is really just flat. Okay, it's not a hump. Okay, but if we go to the next 2 examples of a cubic function, we have a peak here and a valley here, a valley and a peak here. So those 2 things have, these 2 graphs have 2 extrema. We keep going. Quintic function. Oh, sorry. I'll go back real quick to cubics. Cubics is like x to the 3rd. All right, now moving forward, quartic functions are something like x to the 4th. You can see here there's 1 valley. There's a peak here. Okay, also there's a valley, a peak, and a valley, so this is 3. This has a peak, 2 peaks, and 1 valley. This is also 3, so these are 3. These are 1s. All right, and quintic functions are going to be like x to the 5th. Now there's more than just these 2 types. There's actually a 3rd one in there. We just don't have space for it. Again, this is a lot like the x to the 3rd. There's going to be 0 for this one, for those 2 particular examples of a quintic function, sorry. And this one has a 2 peaks and 2 valleys, where its opposite side has also 2 peaks and 2 valleys. So this has 4 for it. Okay, so let's look at some examples that are a little more descriptive down here. All right, this has the different combinations you can get for a 4th, 5th, and 6th degree polynomial. Okay, so for the first one you can see we have x to the 4th. There is nothing else on it, just x to the 4th. This has 1 valley, so it has 1 extrema. different equation, still x to the fourth. All right, but in this case, it has 2 valleys and 1 peak, and it has 3 extrema. Okay, now we're going through this. You can see this young lady here. She says, don't forget to look for relationships. So what we're going to look for relationships by is the degree of our polynomial, the number of our extrema. So if we can see a pattern as we go through this. Okay, so here we have a 5th degree. So x to the 5th. Again, it looks like there are 0 extrema here because there's no peak or valley. The next one, another x to the 5th, but now a little bit bigger of equation. It has 1 peak and 1 valley. It has 2 extrema. And an even bigger equation, we have 2 peaks and 2 valleys for 4 extrema. Again, paying attention to the number of degrees in the polynomial and the number of extrema that we have. Okay. Last example here is the 6th degree. So x to the 6th is just 1 extrema. It's got a 1 valley. A little bit bigger equation with more stuff in it. We have 2 valleys and 1 peak for a grand total of 3. Lastly, a little bit bigger equation. We have a valley, a peak, a valley. This one's kind of hard to see because it's small, but there is a peak there and another valley there. That gives a grand total of 5 extrema. Again, paying attention to this degree of polynomial and the number of extrema. Okay, so some things you should notice. It says it down here, list any observations you notice about the possible number of extrema and the degree of the polynomial. Okay, so what you should notice here is the largest number of extrema we always had was 1 less than our degree. So for the 4th degree, the most extrema we had was 3. For the 5th degree, it was 4, and the 6th degree, it was 5. So the number of extrema is at most 1 less than the degree of the polynomial. Okay, now you'll notice I put the at most. Okay, because in these examples, you'll notice that we had multiple extrema examples, okay, for one particular degree. All right, a 5th degree had 3 different extreme examples. A 6th degree had 3. 4th degree only had 2. But you should notice something about the numbers of these. So 4th degree has 1 and 3. 5th degree has 0, 2, 4. 6th degree is 1, 3, 5. There's some kind of pattern there. Okay? And the pattern is they're either evens or odds. Okay? So an even degree polynomial has an odd values for its number of extrema. Okay? So even degrees have odd extrema, where odd degrees have even extrema. Okay. You'll also notice something about this is the number of extrema never go less than 0. We do have 0, but in other words less than 0, because you can't have negative highs or low points. Okay. So they're going to be, both of these can go as low as 0, but not less. Okay, so for the even degrees, you can go all the odd numbers. So for the 6th degree, we saw we had 5, 3, and 1. It's always got to be an odd number, so it can't be less than 0, so it doesn't go to 0, because 0 is an even number. But the 5th degree is the even number, so you got 4, 2, and 0. Okay. So if we look at just the degrees of a polynomial, we can kind of guess, how many extrema it might have, which is the next piece. Okay, So if we sketch a graph for a ninth degree and look at how many number of extrema it might have, we can start figuring that out. So you take 1 away from the degree. So if it's a ninth degree, you take 1 away. It could be 8. And then because it's an odd degree, it's going to have even numbers for its extrema. So we have 8. It could have 6. It could have 4. It could have 2. It could have 0. Okay. So we can put down our graph with any of those numbers of extrema. Let's put down 8 just because we're going to have some fun. So we have 1, 2, 3, 4, 5, 6, 7, and 8. I almost lost it. Okay, so let's count them. 1, 2, 3, 4, 5, 6, 7, 8. There's an example of a graph for a ninth degree polynomial. It has 8 extrema, so that works out. For a 12th degree, okay, again, we take 1 away from the number of the degree. So in this time, we have 12 minus 1 is 11. And you're going to do all the odd numbers till you get to 0. Okay, so you're going to have 11, 9, 7, 5, 3, and 1. And we can't go past 0, and it's not, 0 is not an even or an odd number, so you're stuck at 1. So those are all the number of extrema that a 12th degree polynomial might have. And we're going to make not 11 extrema here because that's just a pain in the butt of a graph. So let's do just a few. So we got 1, 2, 3, 4, 5. Oh, 1, 2, 3, 4. I missed one. 5. There we go. So you got 1, 2, 3, 4, 5 extrema. And that would be a 12th degree, might be a 12th degree polynomial. All right, one thing you can notice right here when we do these two problems, all right, this has probably been addressed in another part of the intercession course, but odd degree polynomials are going to start and end in different directions. So notice how the ninth degree starts at the bottom and goes up. Whereas even degree polynomials are going to start and end in the same direction. So this one starts at the bottom and goes down to the bottom. Okay, so that's one thing you can help yourself with. You're doing your graphs if you not sure how many extrema, but you know it's an even degree polynomial. Might go down, or then both might go up. Versus an odd degree, they're going to go off in different directions. Okay. All right, here we go. Determine the number of possible extrema and the following polynomials. So, just like we did before, 8th degree means you can subtract 1 from 8. You're going to have either 7, 5, 3, or 1. All right. A quartic function is going to be a 4th degree power, so that's something like x to the 4th. Okay, which means we're going to have either 3 or 1. A 13th degree, subtract 1 from 13, you're going to get 12, and then do all the the even numbers. 10, 8, 6, 4, 2, or 0. The 7th degree, you're going to subtract 1 from 7, you're going to get either 6, 4, 2, or 0. Okay, so we have here, we have matching the graph with its description on the right. So let's do the description. So an even degree function with 2 roots. So a root is where the graph crosses the x-axis twice. And an even degree means it's going to be a graph where it starts and ends in the same direction. Okay, so if it starts and ends in the same direction, it can either be A or it could be C, because B and D start and end in different directions. So which one of these between A and C has only 2 roots? So 2 times where it goes through the x-axis, and that is A. Here's the first one, here's the second one. C hits the x-axis 3 times. There's 1, 2, and 3. So it can't be C. So this is going to be 1. Okay, get rid of those. So a cubic function with 2 extrema. So a 2 extrema is going to have 1 peak and 1 valley. All right, well, that's going to be this one, and it's a cubic function, so it's an odd degree, which means it's going to start and end in different directions. So it's either B or D. Well, D doesn't have any extrema, but B does. So this is 2. Oops. Okay. A quartic function with 3 roots is a even degree which means it's going to be C, because that's going to go up and down. Or sorry, it's going to be both the start and the finish of the graph is going to be either going it's going to be going the same direction. I'll get it. So this is 3, and that means this has to be 4. So a cubic function with no extrema, and that's what D is like. There's no extrema, there's no peak or valley. All right, here's the last question for these notes. Which graph below could represent a cubic function with exactly 3 zeros? So we're looking for a cubic function. So it is a function that has a third degree power, like x to the third. So it means it's going to have the start and end of the graph are going to be going in opposite directions, which automatically takes a out of the equation because it starts and finishes in the same direction. So it can't be that one. Okay, and 3 zeros means it has 3 x-intercepts. So it crosses at 3 spots on the x-axis. So it can't be this one. So it must be B. And there you go. Okie dokie. And that's it.